Welcome, ladies and gentlemen, to Fiske Planetarium. My name is Nicholas. I am the lead operator here at Fiske Planetarium, and I welcome you tonight to Jeff Bennett's talk, What is Relativity? Now, tonight we're going to sort of a pacing of light and dark sometimes as we switch between Jeff's PowerPoint and some more of the full dome feature. Fiske is actually the highest resolution theater in the entire world right now. So it doesn't get better than this. It's literally, this is the best, this is the highest resolution you can find anywhere on the planet. It's only tied with 2 or 3 other planetariums, and so we're all tied for first place. I think, though, we're the best, clearly. I'm biased, though. Now, our speaker would like to ask if you could please make sure to keep your cell phones off. Don't take them out. And if you find that the cell phones are far too distracting, then we invite you to go watch it out in the lobby, which will be streaming it out there too. We're streaming online, so welcome to all of our online viewers as well. Now, Dr. Jeffrey Bennett has been an educator here at the University of Colorado for many years. He's also been the co-creator of the scale model solar system that we have out there along the planetarium, and the one at the in Washington, D.C. The one that's like 1/10,000,000th the scale, so it's a very small scaled down solar system. You can go walk it yourself right after this talk. You can see the little sun is the size of a grapefruit, and all the planets are in scale with it. Now, he also, if you are an astronomy student here at the university, you might know his textbook, The Cosmic Perspective. He's one of the co-authors of that. The Cosmic Perspective is, well, the astronomy textbook I was using when I was an undergraduate. I have to say it's a great textbook. He also is, of course, though, the writer of a number of great children's books, including Max Goes to the Moon, Max Goes to Mars, Max Goes to Jupiter. And, of course, now his new book is out. Without further ado, though, let's give a warm welcome to our speaker, Dr. Jeffrey Bennett.
Well, thank you very much for coming out tonight. When we decided to do this talk, I thought it would be like all my other talks where I kind of have to pay my friends to show up. But I don't even have this many friends, so you must have actually decided to come, and I really appreciate it. Although, as one of my friends pointed out, they're probably not coming for me, you're coming for Albert, so he deserves it much more. So thank you again for coming. Also want to welcome our online audience. We are streaming this live, and thank you to Keenan Brew and Icosa Media for doing our videography tonight. If you want to watch it or tell people about it later, it'll be hosted on the Big Kids Science channel. And if you are watching from somewhere else, maybe you can throw up a comment or something so that we'll know somebody actually tuned in. Otherwise, we'll think nobody was there. So tonight, what we're going to do is I'm going to try to answer this question for you: what is relativity, in a very basic way. And I can give you a short answer to the question right away. The short answer to the question is that relativity is our modern scientific theory that explains the nature of space, time, and gravity. If you think about it, space, time, and gravity covers a lot of ground. So it really is integral to our entire understanding of physics, astronomy, and the universe. It is a very, very important part of modern science. And yet, for some reason, very few people know very much about relativity, even though almost everyone has heard of Einstein and the theory of relativity. So my goal tonight is to give you at a very basic level a quick, and it's going to go very fast, overview of what Einstein's theory tells us. Now, the timing of tonight's talk is not an accident. This year, 2015, is the 100th anniversary of the publication of Einstein's general theory of relativity. So this is not new science. This is not new physics. It's been around for a century already. And that's part of the reason why it seemed to me that it was a good time to make sure that everyone who's heard of Einstein and relativity gets to hear a little bit about what it actually means and why it's so important to us. And as a result of that, I decided with these talks here in Fiske to start out on what I'm calling my relativity tour. And you can see I have a few more locations lined up after this. And for anyone out there watching online, if you would like me to come to wherever you are, just send me an email and maybe we can work it out. Relativity, it's the 100th anniversary, but it's also gotten a lot of popular attention recently thanks to this movie, Interstellar. How many people have seen it? Okay. Perhaps you realize, some people don't realize it, that this movie is actually very much about relativity and what it means. The executive producer of this movie is a Caltech physicist named Kip Thorne, who is one of the leading experts in the world on the theory of relativity. So he really worked hard to make sure that they got the scientific ideas in there essentially correct. And so it's very much worth seeing the movie if you haven't already. And if you do see the movie, or if you saw it already, I would urge you to go take a look at my blog page where I wrote a little post on what's real and what's not real in the movie. So with that, we're ready to start in on relativity. One of the most famous things about relativity is its prediction of the existence of something called black holes. So I thought we'd start out with a multiple choice question. Excuse me. Imagine that the sun magically collapsed into a black hole, retaining the same mass. Earth would, A, be sucked into the black hole, B, become cold and dark, but its orbit would stay the same, C, orbit faster but at the same distance, or D, slowly spiral inward into an orbit about the size of Mercury's. Now, I'm not going to make you raise your hand and commit to a particular answer. However, you probably know that if you ask this question of most people, the most common answer that you will get is A, that if the sun were to suddenly turn into a black hole, Earth would be sucked in. Einstein's theory of relativity, I told you, was a theory of gravity, but it was not our first theory of gravity. Our first theory of gravity actually goes back to Isaac Newton. And Isaac Newton's theory of gravity works really, really well. It explains the orbits of the planets. It explains the orbits of spacecraft. We can direct spacecraft to land on other worlds just using Newton's law of gravity. Now, it's true that Einstein's theory modifies Newton's law of gravity a little bit, particularly in cases of very strong gravitational fields. But out here where the Earth is orbiting the sun, it's a relatively weak gravitational field out here. And Einstein's theory and Newton's theory tell us basically the same thing out here. So we might start out thinking about this question by asking, what would Newton tell us about if the sun suddenly turned into a black hole? Well, Newton's theory of gravity tells us that under the law of gravity, there are three basic types of orbit that are allowed: ellipses, parabolas, and hyperbolas. Now, ellipses are the kind that you're familiar with, things that go round and round and round. Parabolas and hyperbolas are these shapes that come in once, go back out. So you might not think of that as orbiting when something comes in just one time and goes back out, but it's still technically an orbit. And there it is. That's what Newton's theory tells us. The three allowed orbits are ellipses, parabolas, and hyperbolas. And I want you to notice that sucking is not on the list. And so if you chose answer A, that Earth would get sucked into the black hole, that is incorrect. And so one of the first lessons I want you to take away tonight, and something that's a common misconception that people hold about relativity, I want you to remember that, in fact, black holes don't suck. They're actually really cool, and they don't suck. Now, so what would happen? Well, if the sun magically turned into a black hole and retained the same mass, out here at Earth's distance, the Earth wouldn't notice any change, other than it would become cold and dark. So the Earth's orbit would stay the same. With the sun no longer shining, it would be cold and dark, but that's the correct answer to the question. Incidentally, In the movie Interstellar, they do a very nice job of this because if you've seen the movie, and this is not a big spoiler if you haven't, don't worry, but if you've seen the movie, you'll notice that they go to this place where there's this supermassive black hole, and their spacecraft and the planets orbit around the black hole. They do not get sucked in, so they do that correctly. And in fact, the only place they make a very minor error is that as the guy goes falling into the black hole, flying directly into it, one of the other crew people says, oh, he's getting sucked into the black hole. Well, he's not really getting sucked into the black hole. He aimed himself at it, and therefore he's falling in. And the visual that they do in the movie actually captures what really goes on pretty nicely, but it turns out we have a remarkable animation of this, simulation of it, from a movie called, planetarium show called Black Holes, The Other Side of Infinity, which was actually written by the University of Colorado's Andrew Hamilton, another one of the world's leading experts in relativity. And we've got a little clip here to show you about what it's like if you're falling towards a black hole using a kayak and a river as an analogy. So if we can put that up.
A black hole is literally a puncture in the fabric of space-time. Venture closer, and gravity becomes a riptide. It's like riding a raging river that's pulling you faster and faster toward the waterfall.
All right, so I love that little clip because it shows you the idea is that far from the black hole, Einstein's theory gives us the same results as Newton's theory. Far from the black hole, it's just normal orbits. But when you get very, very close, something different is happening with space and time near the black hole, according to Einstein, where space is actually sort of flowing into the black hole like that river. And so if you make the decision to aim yourself right at the black hole, you will at some point be on that flow and going into it. Now, some people might say, oh, the black hole sucked me in, but it didn't, because black holes don't suck. If you're in a kayak and you go over a waterfall, don't blame it on the pool at the bottom. It didn't suck you in. You fell in. It was your own fault. And same thing if you aim yourself directly at a black hole. Now anyway, so black holes don't suck. What do they do? Well, I don't have time to go into detail tonight. I can only pick a few things to talk about, but I do hope you'll take a look at my book and you'll see what would happen on a real trip to a black hole. But for tonight, what I want to do is focus a little more generally on the question, what is relativity? So to start out with, the theory of relativity is actually a theory that was done in two parts. Einstein published the first part, called the special theory of relativity, in 1905. The second part, as I mentioned, in 1915, the general theory of relativity. Now, one question that a lot of people ask is, why did he call it special? Did he think it was really that special? And the answer is no. Special, in this case, is referring to special case. In other words, he did the special theory of relativity. It's the special case in which we ignore any effects of gravity. Now you might ask, why did he choose to ignore the effects of gravity? Well, because it's easier that way. So you do the special theory without gravity first, and then the general theory ended up coming later. Now I want to talk a little bit about what we mean by these words, theory of relativity, and let's start first with the word theory. In science, the word theory means something a little different than what we usually think of in our everyday lives. In our everyday lives, we tend to think of a theory like a guess. But in science, theory is not a guess. Theory is something that explains a wide variety of observed facts in terms of a few simple underlying principles. It makes predictions that have been confirmed, and it's been borne out by repeated and varied testing. So in other words, in science, the idea of a theory is basically something that has been so solidly explored and tested and explained so much that really we couldn't ever find a theory to be completely wrong. We might find that a theory is incomplete, but the answers that it gave us weren't wrong. And Newton's theory and how it leads into Einstein's is a good example of that. Again, Newton's theory of gravity works really, really well. And in all those cases where it works really, really well, Einstein's theory gives essentially the same answers. It's only under some conditions in which Newton's theory begins to break down, like very, very strong gravity, that we need Einstein's theory. But Newton's theory of gravity wasn't wrong, it just turned out not to be the entire story. Now, the second part of the question, or the term, theory of relativity, is relativity. So you might wonder, what do we mean by relativity? Well, the common misconception is that Einstein said that everything is relative. Einstein did not say that. He was speaking very specifically of what we call the relativity of motion, which leads into some other relativity of time and space that we'll talk about. But I want to start out by talking about this relativity of motion. And if you look at me right now, you may think that I am walking back and forth across the stage. But if motion is relative, the way Einstein says it is, then I could say, no, I'm not moving back and forth across the stage. I am staying still, but I'm forced to move my legs because the stage is moving back and forth underneath me. Now, you can probably see how that idea makes a little bit of sense, but for a lot of people, that's a little bit hard to understand. So I want to try another example to explain what we mean by the relativity of motion, and it's up here. So the idea is, I want you to imagine that I get into an airplane and I take off from Nairobi here and I fly to Quito over here and I fly at a speed of 1,670 kilometers per hour. So my airplane takes off in Nairobi, goes to Quito at a speed of 1,600 kilometers per hour, and now I have a question for you. How fast was I going? Now, you may think it's kind of a dumb question since I just told you that I was going 1,670 kilometers per hour. But imagine that kind of like it looks like here, or as we'll see on our Earth over here, imagine that you're watching from the moon. And so I get over here in Nairobi, take off, and what happens? The Earth is always rotating, right? And I didn't choose this speed by accident. It turns out that 1,670 kilometers per hour is Earth's equatorial rotation speed. And so if you watch my flight from the moon, just as we just saw there, you would see me lift off the ground in Nairobi and just stay there. Can we do that one more time, Nick? So I lift off the ground in Nairobi, and I just stay there in the air, and then when Quito arrives, I drop down. Got it? So as viewed from the moon, my airplane just takes straight off the ground, doesn't go anywhere, waits for Quito to arrive, and then sets down. So the question is, which is correct? Did I fly across the Earth at 1,670 kilometers from Nairobi to Quito, or did I go nowhere while the Earth moved underneath me? And you can see from the moon how it would appear that way. And the answer is that relativity tells us that both are correct. What's important is to specify what your motion is relative to. So I did move relative to the surface of the Earth at 1,670 kilometers per hour, but relative to the moon, I was at a speed of 0 while Earth rotated underneath me. And other observers can have other conclusions. For example, aliens watching from far away would see me moving at 800,000 kilometers per hour in my airplane because that's the speed that Earth orbits around the sun. So that's the idea of what we mean by relativity. However, even though it's called the theory of relativity, in a lot of ways it would have been better named the theory of absolutes because Einstein actually based the theory of relativity on his assertion that there are these two absolutes in nature. And the first one is that the laws of nature are the same for everyone. In other words, if you're flying on a smooth flight in an airplane and you toss a ball up in the air in your seat and it comes back down, you won't notice any real difference from what you would notice right here on the ground. And in fact, under any circumstances, if you factor in any turbulence or other things that might be happening, you'll always get the same conclusions about the laws of nature no matter who you are or where you are. The laws of nature are the same for everyone. Now, when Einstein said that this was the case, it was not really a revelation. This is something that had been known for a long time or assumed for a long time, in fact, back to the time of Galileo. And one of the reasons why it was important for Einstein to assert it is because actually there'd been a slight problem that seemed to be coming up with this, which is that a few decades before Einstein started working as the laws of electricity and magnetism were being discovered, at first it kind of seemed like they weren't the same depending on how different people were moving. And Einstein wanted to make sure that the laws of nature were the same for everyone. So part of his goal in the theory of relativity was to restore that. But again, overall, this isn't too surprising. It's the second absolute of relativity that's much more surprising. And the second absolute of relativity is that the speed of light is the same for everyone. Now, it may not sound that surprising when you first hear it, but I want you to think about what it means. So let's imagine I'm in an airplane again, and I'm in an airplane and I'm flying overhead at 500 miles per hour. And let's say I'm sitting back here and I have a friend a few rows up and I toss a ball to that friend. And I toss the ball, according to me, at a speed of 10 miles per hour. What would you see from the ground? Well, you'd see even before I toss the ball is going 500 miles per hour because it's in the airplane with me. When I toss the ball at 10 miles per hour, you add that on and you'll see the ball going at 510 miles per hour. That should make sense. And that's the way it does work, but light, Einstein says, is different. If I'm in that airplane going 500 miles per hour and I turn on a flashlight shining towards someone up in the front, well, I'll say that the flashlight beam is going the speed of light, 300,000 kilometers per second. You would expect, based on what I just told you about the ball, you would expect that you'd say the flashlight beam is going the speed of light plus the 500 miles per hour of the airplane. But that's not what happens. You would still measure exactly the same speed of light. In fact, no matter how things are moving, the speed of light is always the same. This is the key from which all the strange consequences of Einstein's theory of relativity flow. So you might, right off the bat, ask yourself, well, why did Einstein say this was true? Why did he say that the speed of light is the same for everyone? And the basic answer is that it's an experimentally measured fact. In Einstein's time, it had actually already been shown that the speed of light is the same for everyone through something called the famous Michelson-Morley experiment. They didn't quite realize the implications of the experiment themselves. It took Einstein to realize that. But it was showing that the speed of light is always the same for everyone. And in fact, we can test this, and it has been tested in many, many other ways. But the simplest way, or one way that I think will help clarify this idea, we don't do this on a general basis, but when we point our telescopes up and we look at stars, distant galaxies, every one of those stars, every one of those galaxies is moving relative to us. Because of the expansion of the universe, some of the very distant galaxies are moving away from us at a very high percentage of the speed of light. But if you took the light that's coming into your telescope and put it into a device that measured the speed of that light coming into your telescope, you would always find that the light entering your telescope is coming in at exactly the same speed of light, 300,000 kilometers per second. It doesn't ever vary. The speed of light is always the same. And once we have that fact, now we can do what Einstein called thought experiments to try to predict what consequences there would be. Now, I'm going to only have time to do one little thought experiment for you. But I wanted to focus on one of the most famous consequences of relativity. That's also one that most people don't like very much. Maybe you've seen t-shirts like this. 300,000 kilometers per second, it's not just a good idea, it's the law. People don't like to be told that you cannot go faster than the speed of light. Mainly, I think, because we don't like being told what we can and cannot do. But I'm sorry, you cannot go faster than the speed of light. This is not a technological problem. It's not like breaking the sound barrier. We already knew when people broke the sound barrier, some people said you couldn't do it, but that was in engineering, we can't do it. We already knew there were lots of things that go faster than sound. We just didn't think we could do it. But light is different. And here's our little thought experiment. So for our thought experiment, we're going to pretend that I can build a spaceship that can go really as fast as I want, as fast as my imagination can make it go, or your imagination can make it go. So we're not putting any limits on it. The spaceship can go any speed. So I get into my spaceship, I take off going as fast as I possibly can, put it into second gear, go even faster, right? And I'm going as fast as your imagination can possibly allow a spaceship to go. And the only question is, how fast is that? Is there a limit to your imagination? You might think not, but remember, the speed of light is the same for everyone. I'm in my spaceship. I give off light. Now, you might not realize that because people don't glow in the dark, but we do give off infrared light. That's why the infrared camera out in the lobby can pick you up. But let's make it easier. Let's think, I got to see where I'm going, so my spaceship has headlights on it, right? So I've got my headlights shining on my spaceship so that I can see where I'm going. According to me, what are my headlights doing? According to me, they're going at the speed of light, because everyone always measures the same speed of light. I see my headlights going out in front of me at 300,000 kilometers per second. Now, you're watching me, and I'm going as fast as imagination allows possible. But you will notice one thing about me, which is that you can see my headlights and me. And what do you notice about my headlights? Well, you see my headlights are going at the speed of light, 300,000 kilometers per second. You'll also notice that my headlights are going out ahead of me, right? Everybody with me? The headlights are going 300,000 kilometers per second, and they're beating me. Therefore, I am going less than 300,000 kilometers per second. There's no way around this, even though I know many of you are trying to think of a way around it right now. But there's not. If the speed of light really is the same for everyone, then there is no way to get around this logic, this thought experiment. There's no possible way to exceed or even reach the speed of light. We could do similar thought experiments to focus on what that means for time, space, mass, and so on. I don't have time to do those tonight, but I want to just give you one example, another famous example from relativity, which is what we call time dilation. So imagine that I got into a spaceship and took a trip to a star 25 light years away and back, and I traveled at 99% of the speed of light the entire way. Don't try this. If you suddenly accelerated to 99% of the speed of light, you would be killed by the g-forces. So don't actually do this. But if you could, you'd have that trip. And what would you find? Well, because it's 25 light years in each direction and you're going almost the speed of light, for a person on Earth, it has to take you slightly over 25 years in each direction, which means on Earth, a little more than 50 years will pass. But for you, you will find time is running slower on your spaceship than it is back on Earth, at least for the overall journey. And so when you return, only 7 years will have passed for you on your spaceship. So you'll leave in the year 2020. You'll come back having aged 7 years, eaten 7 years worth of meals, had 7 years worth of heartbeats, but it will be the year 2070. That's not an illusion. That is reality. And this is the idea where we say that space and time become intertwined as what we call spacetime. So this is what Einstein's special theory of relativity is telling us. Now you may be thinking, is this all really true? And the answer is it has. Remember, it's a theory, and in science, theory means something that has been tested over and over and over again. This has been tested very carefully and in very many ways, and I'll just give you a few brief examples. We can test it directly. For example, particle accelerators like the Large Hadron Collider pour in enormous amounts of energy to get these subatomic particles moving at very, very high speeds, very close to the speed of light. You pour in a certain amount of energy and they're going 99.99% the speed of light. You pour in a lot more and you get another 9.999%, and so on. Well, right off the bat, as you keep pouring more and more energy in, you get closer and closer to the speed of light, but guess what? No particles ever reached it, none ever has ever exceeded it. That's experimental evidence that you really can't reach the speed of light. You can also test what happens to these particles there. For example, there are some subatomic particles that fall apart, decay in a characteristic amount of time when they're at rest. If you make the same particle moving at high speed, you find it lasts longer because time is running slow for it. So all of these ideas of relativity have been tested very, very precisely. And they've even been tested at fairly low speeds. If you have precise enough measurements, you can see them happening. But there's more ideas and more ways to test relativity. For example, you've probably heard of this famous equation, E equals mc squared. It stands for energy, mass, and the speed of light, c. And that equation is very famous, and it's actually part of the theory of relativity, in the sense that if the theory of relativity is correct, that equation should be correct, and vice versa. How do we know that E equals mc squared is correct? Well, it explains how atomic bombs and atomic power plants work. It explains how the sun shines. So every time you go outside on a sunny day and you feel the sun shining on your body, you're actually testing Einstein's theory of relativity and confirming that it is correct. And you'll remember that I also told you that Einstein was solving part of the first absolute. He was trying to address this problem that had come up with the laws of electricity and magnetism. In fact, his paper on special relativity was actually titled as being about solving the problems of electricity and magnetism. And so what he found was that the laws of electricity and magnetism are sort of embedded within relativity, and again, vice versa. So in that sense, every time you use an electronic device, a radio, a cell phone, your TV, a computer, you're also testing Einstein's special theory of relativity. So this theory is on very, very solid ground. And that brings us to the question of, how do you deal with it? For a lot of people, being told you can't go faster than the speed of light, time is different for different observers, space and time are intertwined, they're so weird that people react badly. They say, I can't deal with that, it violates my common sense. Don't say that. It doesn't violate your common sense. Why not? Because when it comes to these ideas, you do not have any common sense. Common sense, by definition, means things that we commonly experience. The strange effects of relativity are only noticeable at very, very high speeds, speeds close to the speed of light. We don't travel at those speeds. Our fastest spaceship, the New Horizons spacecraft, which will fly past Pluto this July, is going at 50,000 kilometers per hour. It's the fastest vehicle people have ever built. That's like 1/10,000th of the speed of light. We don't ever travel at high speeds, and therefore we can't possibly have any common sense for high speeds. What you need to do is develop a new common sense that will accommodate these high speeds if you want to get comfortable with these ideas of relativity. And this, in a sense, is the hard part if you want to understand relativity better. But what I'll tell you is it's not that hard because you've done it before. Everybody point up. Point down. Okay, that's common sense, right? Up, down. That's good common sense. You can make sure you stand upright with it, and you can even play basketball and so on with it. But guess what? It's not perfect common sense. Well, it's pretty perfect as common sense goes, but it's limited common sense. Because you might remember this. Somewhere back in second grade or so, You had this common sense. You knew that that was up and that was down, and you saw a globe in the classroom, and you ran to your teacher and said, man, those people are in trouble. What are they going to do? Because they were going to fall off. What happened? You realized that your common sense for this small region of Earth, like this room, it's very good. It works really well for this small region, but you can't extend it to the entire globe. For the entire globe, you have to change your common sense to up being away from the center of the Earth and down being toward it. And you did that. This is very familiar to you now. In the same way, if you're willing to spend a little bit of time, it doesn't take a ton of time. If you want to become an expert, it takes a lot of time. But if you want to just get the ideas, a little bit of time working through the thought experiments, thinking about these ideas of relativity, and it can start to become your new common sense for the way that space and time really work. Now, I told you we were going to move fast, and that's all I'm going to say about special relativity tonight, because I want to jump ahead and start talking a little bit about general relativity. Now, general relativity is where Einstein brought in gravity. After he finished special relativity in 1905, a lot of other physicists had been working on some of the same issues, because these problems with electricity and magnetism that he was solving were known to others. And in fact, a lot of historians of science think that if Einstein had not published the special theory of relativity when he did in 1905, that someone else likely would have gotten the same theory, perhaps within just a few months later. People were working on this. It was an idea that was ready to happen. But once Einstein published special relativity, it seemed like he'd solved all the major problems that were out there. But he didn't think he was done. So he kept working. And with general relativity, he really kind of jumped ahead of where everyone else was. Now, he had a lot of reasons why he didn't think he was done when most other people thought that he was. But it's worth starting out by thinking about, the question of, does gravity, as Newton had described it, make sense? So does Newton's theory of gravity actually make sense? Now, it clearly works. It works really, really well. And in fact, I'll tell you a little story. So after Newton had published his laws, his book Principia, his law of gravity, it seemed to be working really, really well, but it hadn't been around that long, century plus, when the planet Uranus was discovered in the late 1700s. And as astronomers watched the planet Uranus in its orbit, they began to notice after a few decades that Uranus was not moving exactly the way Newton's law of gravity predicted that it should. It was very close, but it sometimes was moving a little bit faster or slower than it seemed like it should be. So there were a fair number of physicists who thought, well, maybe Newton's law of gravity, maybe it's not quite exactly right. Well, in the 1840s, there were a couple of people, one in particular, a French scientist named Leverrier, Urbain Leverrier, who said, I think Newton's theory is right, but there's something tugging on Uranus that we don't see. So Leverrier did these calculations, assuming that Newton's law of gravity was correct, and he came up with this idea that if there was another planet beyond Uranus that no one had yet discovered, and it was right there, then that would explain Uranus's funny motion. So he did the obvious thing. He had a friend who ran the Berlin Observatory. He wrote a letter to his friend at the Berlin Observatory. He said, why don't you point your telescope right there and see what you see? So the friend got the letter, pointed the telescope right there, and what did he see? Neptune. That's how Neptune was discovered. Neptune was discovered by calculations assuming that Newton's law was correct. Neptune was discovered by physics and mathematics. Incidentally, if you like to read your horoscope, for thousands of years before that, none of the astrologers had noticed that they weren't taking into account one of the planets, Neptune, since it hadn't been discovered. And none of them predicted that there must be another one to explain why their horoscopes weren't working quite right. The astronomers got it on their first try. Leverrier, a couple decades later, turned out there was another little problem. Mercury wasn't moving exactly the way Newton's law of gravity predicted it was. Really, really close, but not quite exact. And Leverrier had another brilliant idea. He said, well, maybe there's another planet that we don't see that's explaining Mercury's orbit. And so he did some calculations. He said, you know what? We could explain Mercury's orbit if there's another planet that's in exactly the same orbit as Earth, but on exactly the opposite side of the sun. So we'd never see it because it was on the other side of the sun. That planet does not exist. But Leverrier gave it a name, and in name it lives on because Leverrier called the planet Vulcan. So you may remember with the sad passing of Mr. Spock last week, that's his home world, so it lives on in Star Trek. Well, so if that planet doesn't exist, why does Mercury not move exactly the way Newton's laws predicts? Well, Einstein actually solved that one. When you take into account what he discovered about gravity, he does explain the orbit of Mercury. But that wasn't initially what was bothering him, and other people didn't see that as that big of a deal. Einstein was more troubled by a few other things, including this does it make sense question. So why do I ask, does it make sense? Well, Newton's law of gravity tells us that, let's say, we got the sun and we got the earth. And the sun has gravity, gravity acts between them, and it makes the earth go around the sun. Now think about that. The sun and the earth are 150 billion kilometers apart. They don't have eyes, they don't have ears, they don't have sense of smell. How does the sun know the earth is there and vice versa? How can it be that across this great distance they respond to one another? Well, think about that. Here's what, a famous scientist said about this idea. That one body may act upon another at a distance through a vacuum, and force may be conveyed from one to another, right, like the sun to the earth, is to me so great an absurdity that I believe no man who has a competent faculty in thinking can ever fall into it. So basically, this famous scientist is telling you, if you think gravity works the way Newton's law of gravity says it does, and that it just happens that way, I mean, it does seem to work, but man, that's completely ridiculous and absurd. I don't know if that's what Einstein actually thought, because he didn't say this. This is a quote from Newton himself, recognizing that even though his law of gravity works so well, it doesn't really seem to make any sense. So what did Einstein do about this? Well, I want to tell you a little tale. So the tale is a tale of two travelers. So you're imagine that you live a long, long time ago at a time when you believe the earth is flat. And you're a wealthy patron of the sciences, and you say, let's do some exploring. So you hire two explorers, and you say to them, you go that way, and you go that way. And don't come back until you discover something really extraordinary. So your two travelers go off in opposite directions. Sometime later, they come back. Both at the same time. Seems a little coincidental, but they both come back. You say, oh, you both back. What'd you discover? We ran into each other. Now, if you truly believe that the earth is flat, this would seem really crazy, wouldn't it? But of course, we know what happens. The earth is not flat. The earth is round, so when you send off your two explorers, of course they're going to meet. Imagine that sometime later, your two space probes ran into each other. Would you be surprised? You shouldn't be. You shouldn't be, no. Because it happens, well, it doesn't happen all the time, but it could in principle happen all the time. For example, if you're in the space station and you send one probe in one direction, the other probe in the other direction, well, they're going to meet up on the other side of the earth, right? Why? Well, because they're orbiting. And why are they orbiting? Well, because of gravity. And how do they know to orbit because of gravity? Well, because it's this magical force that acts across a distance, in this magical way that Newton was talking about. Think about the two pictures we've just seen. The one of the Earth, the travelers going around the Earth, and the one here. Other than that, this one's above the Earth and that one was down the surface. It looks pretty similar, doesn't it? So you might ask yourself, why is it that for the first one, we say they met because the Earth is curved, and for this one, we say they met because of a magical force that acts across distances? Why don't we just say space is curved?
Scientists used to think of gravity as some kind of mysterious power that objects like the sun project across space. But what if it's space itself that gives gravity its pull? That's the way one man saw it. To Albert Einstein, space is a bendable, four-dimensional fabric he called space-time. And gravity? That's the warping of the fabric by massive bodies. They literally put a dent in space-time. Objects get caught in their groove and simply drop into orbit. Einstein's theory was a radical notion, all the more when taken to its extreme.
In the movie Interstellar, that's why when they get on the planet very close to the black hole, time runs much, much slower on that planet. For us here in Boulder, it means that because we're up at altitude, our time runs a little bit faster than it does down at sea level. Don't let that worry you too much, even though you are, in fact, as a result of it, going to live a shorter life than people at sea level, but fortunately only by about a billionth of a second. If you had a much stronger gravitational field, the time difference would be greater. And this has been measured many, many times by looking at strong gravitational fields in other stars. And even right here in Boulder, over at NIST on baseline, they've measured the difference in the rate that time moves over just a 1 meter difference in height. Gravitational waves are predicted to exist by this theory. And I don't have time to talk in detail about that, but it's the idea that gravity, the information that gravity has in space-time propagates outward as a wave through space-time in much the same way that electromagnetic waves take light propagating out. And most famously, it tells us that you can bend space-time like that movie showed us, and you can bend it more, and you can bend it enough to make what we call a black hole. I hope that you will keep learning more about this. If you do get a chance to read my book, you'll see a lot more thought experiments and details to lead you through these ideas. But for the last couple of minutes, what I want to do is focus on the subtitle for my talk, Why These Ideas Matter. So I want to talk to you about 4 reasons why I think everyone should know something about relativity and why it should matter to all of us. And the first reason is what I call the science reason. We've already talked about the idea that relativity is our theory of space, time, and gravity. So if you're going to do science, if you're going to do physics or astronomy, you have to know relativity. It also has a lot of practical applications. E equals mc squared we talked about, nuclear power, sunshine, your computers. But I'll mention one more, GPS. Your GPS devices are tracking your location off of satellites that are orbiting the Earth. They're orbiting in a fairly high orbit, which means they're at a high enough altitude where their time runs somewhat, very slightly faster than it does down here on the ground. In addition, they're traveling at relatively high speed. So special relativity and general relativity both give you changes in time as a result of where those satellites are located and how fast they're moving. You need to take that into account when you calculate your location using your GPS. Now, fortunately, you personally don't need to take it into account, but your GPS unit is doing that automatically. If it wasn't, if the programming didn't take the changes in time between those satellites and the ground into account, you would be lost, literally. The second reason why I think it's important for everyone to know something about relativity is what I call its effects on our perception. Now, we all live our lives. We maybe don't think too often about these kind of scientific, esoteric ideas, but in some sense, we all have this idea of how we fit in to the entire universe, our place in the universe, your perception of what it means to be human in a vast universe. And you would like your perception to be based on reality. If you still believed, as people did for thousands of years, that Earth was the center of the universe, you'd have a very different concept of reality than what we have today. And today, if you have a concept of reality that still thinks space and time are completely separate instead of intertwined, the way relativity tells us, then again, your perception is not fully based on reality. So if you want to have a real perspective on what it means to live as a human being in this universe, again, it's very important to understand the ideas of relativity. The third reason why I think relativity is so important for everyone to know is because I believe that this theory tells us something very important about human potential. This is really an incredible idea that Einstein came up with, and that has been then experimentally tested out and verified over the next 100 years. It tells us that it is possible for us to do really, truly amazing things through science. We have this incredible potential. And I think Einstein's own story makes this idea even stronger. You probably know that Einstein grew up in Germany. He was Jewish at a time when Hitler was coming to power, and as a result of that, he left Germany, or did not return to Germany when he was in the US at the time. And he lived through these horrible things. He lived through the time of the Holocaust. He lived through the time of World War II. He lived through seeing the nuclear bombs based on E = mc squared that he had come up with used. And yet, despite all these horrible things that he lived through during his lifetime, he always remained an incredible optimist. He was always believing that we could do better, that we would do better. He fought for human rights. He stood up for the rights of people everywhere. Why? What is it that made him so resilient, so optimistic in the face of so much bad things that he saw going on in the world around him? And I think it's because he understood this, because of what he personally had done, that if we put our minds to the positive instead of the negative, we have enormous potential as a species. And the fourth and final reason I'll give you why I believe all of this matters is maybe the most philosophical one, but it's what I call your indelible mark on the universe. And we haven't had enough time to go into great detail to make all of this real clear, but you probably start to get the sense from the things I did talk about that this idea of space-time is very different from our ordinary ideas in which we just move through time. Space and time are intertwined, and the way that little video showed you, there's sort of like a fabric to space-time. The events of space-time. Once something happens, once there is an event, it becomes sort of permanent in space-time. In the movie Interstellar, if you've gotten to see that, towards the end of the movie when he's moving around there, it's kind of giving you that idea that events are always there, and if you had the ability as a multidimensional being, you could, in a sense, move about them. That idea has been worked out before by others. Kurt Vonnegut, if you've ever read his book Slaughterhouse-Five, talks about the same general principle. But this idea that events are permanent, that they become part of the fabric of space-time, to me is very, very important. If, for example, in second grade, maybe you weren't very nice and you hit the kid sitting next to you, but the teacher didn't see it and you denied it, and you didn't get in trouble. You might think, hey, good, lucky me, I didn't get in trouble for what I did in second grade. But a multidimensional being moving around through space-time could, in principle, at any moment, whatever moment means in four-dimensional space-time, go look at where you were in second grade, and guess what they'll see? You've been caught. It's not gone. It happened. It is permanent. It is a part of the fabric of the universe. So I want to close with, I'll just close with the final words from my book. Your life is a series of events, and this means that when you put them all together, you are creating your own indelible mark on the universe. Perhaps if everyone understood that, we might all be a little more careful to make sure that the mark we leave is one that we are proud of. So I will stop there. Thank you very much. So we will have a bunch of time for questions. I want to just show you one other little thing because it's, for me, kind of cool. You can read what it says up there. I'm not quite sure how this happened, but I got a phone call a few years back from an astronaut named Alvin Drew asking if I would mind if he read my book on the space shuttle. It wasn't very hard to answer that question. Once I realized he was for real and not somebody playing a joke on me. And as a result of that, my 5 children's books were launched last January to the International Space Station. They're actually still up there. They've all been read in English now. We have just a very brief clip to show you.
Hi, I'm NASA astronaut Mike Hopkins on board the International Space Station, and it's one of my favorite times. It's story time from space. Now today's story is Max Goes to the Moon, a science adventure with Max the dog.
So, thanks. So I'll encourage you all to go to storytimefromspace.com. So far only one of the videos is posted, but hopefully the rest, lots of curriculum materials will go up there eventually. And by the way, the reason only one video is posted is because the program, even though they've launched the books into space and that costs money and the astronauts are reading them, there's no money for actually doing things like video editing and curriculum development. So you can also click the little donate button that you'll see there. That would be very, very helpful. And those are the rest of my books. This book, there's a few copies that I have at the ticket office if anybody wants one. And those are the children's books that are up in space. I have one on the search for extraterrestrial life, on math education and science education, and that's all I need to say. So thank you very much, and we can take questions. I can hang out for questions for as long as you want. If you get bored, I won't feel bad if you get up to leave. Thank you. I'll try to see you even with this light shining in my eyes, but if you're in a place where I can't see a hand up, you might have to move around where I can see you. I don't see any hands yet. Where are the hands? Is there one? Okay.
So people have found limitations on Newtonian physics, right? So are there any limitations on the general theory of relativity?
Very good question. Are there any limitations on the general theory of relativity in the same way that there are limitations on Newton's laws of physics? The answer is yes. There is at least one place where we know that there's something that we don't know, right? It's the known unknowns, right? General relativity is essentially our theory of the large-scale universe, big things in the universe. There's also a theory called quantum mechanics that's basically the theory of the very small. And it also has been very well tested and passed every test that we've given it so far. However, there is a place, and that place is the singularity of a black hole, the very center of a black hole, where quantum mechanics and general relativity essentially give you different predictions about what would be happening there. Now, we have no way to test that because we can't go inside a black hole and see what's actually going on there, but surely they can't both be right if they're giving different predictions. So we do know that either general relativity or quantum mechanics or both must not be the entire story. So what physicists are doing today is they're searching for the way to unify these ideas together, to pull all the laws of nature into one. And in a sense, in the same way that relativity fills in places where Newton's law was incomplete, hopefully, eventually, we'll have what Stephen Hawking likes to call theory of everything, which is where that movie got the name, a theory of everything that will show that relativity was incomplete. Other questions?
Yes, sir. The idea that space-time curves implies perhaps that it might have some sort of substance. I'm curious about your thoughts on that. Is that related in some way to dark matter and dark energy, or is that something completely unrelated?
You know, I think that the question of a sort of a substance, we use this terminology of a fabric of space-time just because it's the only way we can visualize it. You know, we can't, if 3 dimensions are curved, since we're living in 3 dimensions, we have no way to visualize that. So the only way we can visualize it is by taking a 2-dimensional thing and using an analogy where we curve it. So we think about fabric or paper or something. But I wouldn't take that too literally, and the scientists don't take that too literally. As far as dark matter and dark energy, probably not, but maybe, you know, dark matter and dark energy are these 2 huge mysteries in science today. So dark matter, like I showed you that picture of the cluster of galaxies that's bending the light. Well, if you count up how much mass there is that you can see in those galaxies, it's not enough to explain how much the light is bent. What you find is that there must be a lot more matter there than meets the eye, like 10 times as much as meets the eye. And since we can't see it, we call it dark matter. But we do not yet know what it is. And dark energy is even more mysterious because we know the universe is expanding. You would expect gravity to be slowing the expansion with time, but we found that instead the expansion is actually accelerating, which means there must be some force or energy that's causing it to accelerate outward. We have no idea what it is, so we just call it dark energy because it sounds nice. But just having a name for something doesn't mean you understand it. And so we do not know what either dark matter or dark energy is. And so since we do not know, I think it's important to be very careful about guessing what they might mean when we discover what they are. So they might turn out to be fairly mundane and fit in with our current physics very nicely, or it might be that they'll point us in the direction of some very new physics.
So I read in a children's book from the public library, a book about Einstein, that when he was a child, that he imagined, or maybe not as a child, but he imagined writing on a beam of light.
Yes, that is the story that Einstein told, that he was, you know, at age sort of 15, 16, he was imagining what it would be like to ride on a beam of light, and he began to encounter these paradoxes of things that would seem strange. So when I told you that the speed of absoluteness of the speed of light is an experimentally verified fact, that's true, but that's not why Einstein latched onto it. It was because he realized it was the only way to solve these logical paradoxes that he was running into.
Well, that made me wonder, so if we do the trip that takes 50 light years, and it feels like 7 years to you, but 25 years to the Earth observer, how long does it, if a photon had feeling, how long would it take?
Oh, that's one of my favorite questions. Now, if a photon had feeling, what would it notice? You know, if a photon going at the speed of light, in principle, time never passes, and all distances are shrunk to 0. So if a photon had feeling, presumably it would see the entire universe and the entire history of the universe as just a single point. That's a very philosophical idea, and we can't ask any photons to know whether that implication is correct, but it sort of seems to be implied. So yeah, it's a very interesting thing to think about. Yes?
So I know we can't speed up the speed of light, so we can't shoot it from another speed of light. But can you slow it down?
You can slow the speed of light in a substance. And so people do that. So as light passes through a material, it goes at a slower speed. So when we say that the speed of light is absolute, we're talking about the speed of light in a vacuum. Empty space is absolute. But it does go slower in materials. That's why lenses bend light, for example. One more?
Well, I read that a black hole is kind of like a rip in the fabric of space-time. And I know that if you have like a 2-dimensional surface that you're on, and you fall through a hole in the surface, then you fall down through the 3rd dimension. So what if it's the same thing in the 3rd dimension?
Very good question. What does it mean to fall into that rip in space-time?
Yeah, if you fall through a rip, and if you fall through a black hole, what if you're really falling through time?
Well, space and time are intertwined there. So one of the interesting things I didn't have time to talk about on that I told you in the book, I start out with the voyage to the black hole. If you watch someone plunging into a black hole, they will never finish falling in because time comes to a stop at the event horizon, as perceived by the outsider. Now, the person falling in, they just fall right in, and they perceive time to be moving along just normal. So it's a very strange idea. But the idea that when you fall in, where do you fall to? You can start to imagine, well, maybe somehow it could connect up to something else in another part of the universe. And that's, in a sense, what we call a wormhole, that in the movie Interstellar, they talked about wormholes also. So somehow you're going through some multi-higher dimensional space. But physically, what we can study and talk about is the 4 dimensions of space-time. Other dimensions, if they exist, we don't currently have anything that tells us how to deal with them. But I'll just stop right there just so I know a lot of people are ready to go. Thank you very much. And if you want to talk to me some more, you can come on up and I'll be happy to keep talking. Thanks.